again, and welcome back to our From Concept to PCB series. In the previous video, we explored how to enhance the Raspberry Pi Pico 2 with Wi-Fi using an ESP32 module. We used the CELUS Design Platform to streamline the PCB design process by quickly modifying an existing project, integrating an ESP32 module for Wi-Fi connectivity, and exporting ready-to-use CAD files for your preferred CAD tool. Now it's time to take the next step, integrating these CAD files into Autodesk Fusion to finish your PCB designs. On this video, we'll cover the full process of preparing your design for manufacturing. First, we'll import a CELUS-generated schematic into Autodesk Fusion and validate it. After, we'll dive into PCB Layout and Routing, including how to edit layout design rules to match your PCB manufacturer capabilities, ensuring your board meets design and performance standards. And finally, we'll generate a 3D model of your PCB to enable seamless integration with other PCBs, mechanical parts, and enclosures. As you may know, Autodesk Eagle will be deprecated on the 7th of June 2026. This means that Eagle users should start transitioning to Autodesk Fusion. The good news is that Eagle design files are fully compatible with Autodesk Fusion, making the transition seamless. You can import your existing Eagle projects directly into Fusion Electronics Design Workspace, ensuring that your previous work is preserved while taking advantage of Fusion advanced features like PCB 3D model generation, mechanical integration, simulation, and cloud collaboration. Autodesk Fusion is an all-in-one design platform that combines electronic and mechanical design tools in the cloud. With built-in electronic and mechanical design tools, Autodesk Fusion is more than just a PCB or 3D design tool. By using Autodesk Fusion, you can generate 3D previews of your PCBs, allowing you to spot potential design issues before manufacturing. Also, it's really cool to see a 3D preview of what your board will look like beforehand. You can even create realistic renders of your design. You can integrate mechanical and electronical designs, ensuring your circuit board fits perfectly into its mechanical enclosure, reducing errors and improving efficiency. Improve the reliability of your PCB by making electromagnetic analysis using the signal integrity extension, making sure you meet electromagnetic compatibility and interference standards before manufacturing your board. You can also make stress and thermal simulations to identify the risk of failure due to part overheating on your PCB. Using Fusion cloud-based collaboration tools, you can work as a team using version control, live design reviews, and integrated task management. Enable multidisciplinary teams to collaborate in real time, monitor changes, and manage projects. All these tools help you work smarter, reduce waste, and get your product ready to manufacturing faster. Adding the fast schematic generation capability of the CELUS Design Platform and all the PCB design validation tools of Autodesk Fusion, you ensure a fast and efficient production development. Let's start by importing our CELUS-generated CAD files into Autodesk Fusion. First, open your project on the CELUS Design Platform. Navigate to the output files and select Autodesk Eagle as your output format. Click on the Download button, which will generate an Eagle schematic file that we are going to use to import into Autodesk Fusion. Now open Autodesk Fusion to import our Eagle schematic file into it. On the File menu, click Upload. Then click on Select Files and browse for the schematic file we just downloaded. Once you click Upload, you'll see a prompt asking you if you want to create an electronic design file. An electronic design file links your schematic file with your PCB file. Click OK to proceed. You'll see two files being uploaded on the data panel on the left. Once these files are uploaded, double-click the schematic file to open it. You can open the Sheets panel on the bottom to navigate the different schematic pages. Each page represents the schematic of the cubes we just selected earlier on the CELUS Design Platform. We could start designing our board directly from the schematic, but this would mean that you wouldn't be able to edit the components inside the schematic. To solve this, I will show you how to generate a Fusion Hub library from the schematic and how to update this schematic to use those same libraries. This will ensure that you can make customization to the components to fit your needs and preferences. To generate our libraries, we are going to click on Library on the top banner. Click on Export Libraries. Select Merge into one library to avoid multiple libraries being created and to keep all your components onto the same library on Fusion Hub. Click OK, and the dialog will appear for you to select the location of your new library. Simply click Upload to save the library on the current location. You'll see that a new library file will appear on the data panel. Once the file is uploaded, you can double-click it to open the library. So now we have exported the components in our schematic into a Fusion Hub library. However, the components on our schematic are not yet linked to the ones created on this library. To be able to edit the components in our schematic, we'll first need to replace the libraries in the schematic with this newly created library. Go back to the schematic and under the Components tab on the right, click on the first drop-down menu and select In this design. This will filter the shown libraries to include only the libraries used in our design. As you can see, the libraries in our schematic are grayed out, meaning they are not available and you cannot edit the components within them. To replace this library with the one we just created, right-click on one of them and click Swap Library in Design. A prompt will appear for you to select the new target library. Click on the drop-down menu and select our newly created library. As soon as you click Swap, you'll notice that the library icon changes from an hard drive to the Fusion Up symbol, and it's no longer grayed out. This means that the library is available and you can now edit the components within this library. Repeat this process until you have swapped all the libraries in your design. Now that all of our components are linked to the Fusion Hub library, it's easy to edit and update them. To check this up, right-click on any component and click on Edit Component. The component will open in edit mode and you can make any changes that you want. Once you're done editing your component, don't forget to edit it on the schematic. Go to the library panel on the schematic and click on Update Design from all libraries used in the design. This will make sure that your components are up to date with the library. By exporting our libraries and setting them up properly from the beginning, we ensure a smooth workflow, making it easy to edit and manage components. To learn more about Fusion libraries and how to work with them, follow the link in the description. But before moving forward into layout, it's crucial to validate your schematic and make sure no errors are present. Apart from a visual check to the schematic to make sure everything is alright, you should first read the component's datasheet or application notes to make sure that you are following all the manufacturer's requirements and suggestions. CELUS Design Platform is a great tool to avoid having to read tons of datasheets just to find the right components. However, this does not mean you should skip an informed reading of the component's datasheet and other reference materials for the components you have selected. The good news is that you can access the component's datasheets directly from CELUS Design Platform. On your project block diagram, open the Kubo list for the functional block of the Kubo you want to check by right-clicking on it and clicking on Select Kubo. Click on the Info button to open the Kubo, and then go to the Kubo BOM tab. From this tab, you can click on any component to open the component page where you can access the component datasheet. You can also open the Additional Resources tab to check if there are any documents like application notes that might be useful to work with the Kubo. For example, this RP2350 Kubo includes the hardware design guide for working with this microcontroller. This guide provides important information about the schematic capture of the circuit to work with an RP2350 and also some layout considerations which are very important to ensure good signal integrity. You should use all the available information from the manufacturer to make the final validation of your design. This ensures that you won't get any surprises when testing the prototype. Once you've made sure your schematic is well captured, you can do a final check to make sure there are no errors in your schematic by running the electronic rules check. Go to the Validate banner on the top and click on the ERC button. You can then check the error panel on the right. This will show you all the errors and warnings present on the schematic. You can double-click them to highlight the error location. To dismiss any warning or error, you can click on the Approve button on the bottom. You should go through all of these errors and warnings one by one, and either approve them or solve them to ensure schematic quality. Now that our schematic is validated, we can proceed with PCB Layout and Routing. Click on Switch to PCB document on the top banner to create a new layout file from the schematic. You'll see that the layout file will be created with all the components of the schematic placed in the left. We will start our layout by grouping components that belong to the same Kubo together. To do this, go to the schematic, select all the components in one sheet, go back to the layout, and you'll see that the components from that sheet will be selected. Drag and drop them away from the rest of the components and group them together. Repeat this process for all of the sheets in your schematic. Now that we have grouped all the components according to each specific Kubo, let's start by laying out each group individually. Give priority to positions that minimizes track length and layer crossing. Don't forget to follow the manufacturer's layout recommendation if they are available. Now that we have our preliminary layout ready, and before starting routing our PCB, we'll need to configure the design rules like clearances and minimum widths to ensure your design meets your manufacturer capabilities. Go to the Rules banner and click on Design Rules. On this window, you'll see different rules for your design. Some rules regard the clearance between different objects in your design. Other rules are regarding the minimum size of your holes and the minimum width of your copper traces. You should find these rules on your manufacturer's webpage. It's important that you follow these rules to make sure that your design will be manufacturable. Another thing to consider is your design preferences. Under the Rules banner, click on Design Preferences. On this window, you'll be able to define your layer stack, the size of your annular rings, the shape of your pads, and also your thermal isolation and solder mask and stencil clearances. You should update the layer stack properties according to your manufacturer's specifications. Under Annular Ring, you'll see that you can define the different sizes for the annular rings under different conditions. Specify these values according to your preferences and your manufacturer minimum requirements. Once you've updated your design preferences, click OK. Now that we have defined our rules, we are ready to start routing our PCB. Since we are creating a 4-layer board, we will start by adding 2 ground planes to the inner layers. To do this, select the second layer, and under Design, click on Polygon Pour. You can now create a polygon around the area of your board. Since we want to connect this polygon to the ground, I'm going to write ground. This will create a polygon pour connected to the ground. Repeat the same thing for the other internal layer. This will ensure a clean and continuous ground plane, minimizing ground loop areas, since both outer planes will have a ground plane near each other. You may want to apply a different stackup, depending on your application. To know more about 4-layer stackups, check the link in the description. Now it's time to route the other signals. I typically start by the power and ground connections, and then move to other signals. I do the routing iteratively until I reach a design I'm happy with. Don't forget to always follow your manufacturer's instructions and recommendations. Before moving forward, there are a few design considerations that I would like to share with you. Keep the power tracks as wide as possible connected to a single low impedance point. As you can see here, I have my VDD connected to the power output of this power converter by using separate tracks to each side of the board. Keep in mind that you should follow a star connection. This means that all power connections should be connected to the power source by using a single low impedance path. Another thing to take in consideration is decoupling capacitors. Keep decoupling capacitors as close as possible to the device. Make sure to add a via connecting to ground close to each capacitor, making sure all the filtered noise doesn't affect nearby signals. On the power converter side, make sure the power supply's capacitors are close to the power supply chip, as well as they have enough vias connecting them to ground. Another important thing is that you should keep the inductor traces as short as possible, minimizing the switching loop. Regarding the RP2350 microcontroller power supply, make sure to follow the recommended layout described on the hardware guide for the regulator. This includes keeping the inductor loop area as small as possible, adding ground vias to decoupling capacitors, and cutting out the ground plane from the internal layers, making sure switching noise doesn't affect your ground connections. Another thing to keep in mind when designing your ground planes is that you should never cut your ground plane in half. While placing your vias, make sure that they have enough clearance to create a ground connection between them. By doing this, you ensure ground plane continuity. For example, on this case, if I hadn't left enough clearance between these vias, any return current coming from here would have to cross all of these vias instead of being able to have a direct return path. Regarding return paths, make sure that you have enough vias connecting your ground planes to your connector ground. Make sure to keep your noisy signals grounded. I've created this ground ring around this crystal to make sure that any noise doesn't propagate to nearby signals. On the antenna side, make sure to leave all the ground planes away from this area. Adding a ground plane below the antenna would not only shield the antenna from incoming signals, it would also contaminate the ground plane with noise from the antenna. Also make sure that your USB differential signals have the same length. To correct any differences in the length of differential signals, we can create this kind of pattern. This will harmonize the length of the two signals, making sure both signals reach the destination at the same time. To create this pattern, you can use the meander tool. Just select the differential signals you want to work on and start creating an area for your meander. You should see the length difference between both of them. Try to make both signals have the same length. As you can see, both of them are 100% right now, which means that they now have the same length. I can just click, and that's it. I just made both these traces have the same length. Proper routing techniques ensures reliability and minimizes interference or signal degradation. While there are many design practices to follow, It's essential to maintain a critical, creative mindset. Understanding the reasoning behind these rules is important for you to make better design decisions. If you want to enhance your design skills, I recommend checking out this book called The Circuit Designer's Companion. While this book doesn't cover everything in detail, it's an excellent starting point to grasp the fundamental principles of PCB design. You can then dive deeper by searching for additional resources on each topic. Follow the link in the description for an Amazon link of the book. Now that our layout and routing is finished, let's turn this PCB into a 3D CAD model. This will enable you to check if your PCB fits in other mechanical parts, like enclosures, or you can actually use it to create an enclosure around your PCB. To do this, simply click on Push to 3D PCB on the top banner. On the panel that appears on the right, you will see a warning sign in front of components. This means that you are missing 3D models on your components. This is expected since we haven't added 3D models to our components yet. I'll show you how to solve this in a minute. For now, we are going to simply click Push. A new file with the 3D model of your board is going to be created, but as you can see, the 3D model for your components are missing. To solve this, we'll need to add the 3D models of the components into our library. First, we'll need a 3D model of the component. You can download component 3D models from any CAD model provider of your choice, like Ultra Librarian or Component Search Engine, or from your manufacturer's webpage. If you want, you can also generate it yourself using the Fusion package generator. First, open the Fusion electronic library created earlier. Under the Footprints tab on the Content Manager, right-click on the footprints that you want to add the 3D model. Select Create New 3D Model. A Save dialog will appear for you to save your 3D model. I advise you to create a specific folder for all your 3D models. Click on New Folder, name it, select it, and click Save. To create a 3D model using the Fusion Package Generator, you can click on Package Generator on the top banner. Select the type of package you want to generate from the library, and fill in the package dimensions. You can typically find this info on the component datasheet. If you want to add a 3D model from an external source, you'll first need to upload it to the Fusion Cloud. Go to File menu and select Upload. Select the location of the 3D model of the component, change the location to the 3D model folder, and click Upload. Once your file is uploaded, you can drag and drop it to your package design window. This will add a 3D model into the package. Check if the model is well aligned and make adjustments if needed. When you're done, click on the Finished button. Now repeat this process for all the components in the library, and don't forget to hit the Save button once you're done. Now that all of the components have a 3D package associated with them, we can finally add them to our 3D PCB. Go to the PCB Layout file, and on the library banner, click on Update Design from all libraries used in the design. This will update the libraries to include all the 3D packages that we just added. Now click again on Push to 3D PCB, and as you can see, the warning sign has disappeared because all of our components now have a 3D model associated. Click on the Push button to generate the final 3D model with all the 3D components associated with it. This means that you have a full 3D model of your PCB that you can then integrate into your other designs. This ensures that when you update your PCB, anyone will be able to see those changes in the designs your PCB is being used, helping to catch potential design conflicts and make adjustments before manufacturing, reducing prototyping costs. And that's it! We have successfully imported and validated our schematic generated on the CELUS Design Platform into Autodesk Fusion to complete our PCB design. In the next episode, we'll dive deeper into the generation of the manufacturing files you'll need to go from the 3D model we've just created to an actual PCB. I'll show you some tips on how to assemble your PCB, and we'll do the final validation by programming our board. Make sure to like, subscribe, and hit the bell button to make sure you don't miss it. Drop your questions on the comments below, and don't forget, go to app.celus.io or follow the link in the description to start using the CELUS Design Platform to create your own projects. Thanks for watching, and I'll see you on the next episode.